Hello everybody. Now my today is my topic of discussion is 18 electron rule and its applications. 18 electron rule generally play a very vital role to determine the stability of the complex. Generally this term has been introduced in 30 to 40 years ago for determination of a stability of a complexes. Generally different complexes are there which are play a very vital role in a coordination and organometallic chemistry, and the stability of complexes has been determined in a old version. It is determined by using a EAN rule, that is effective atomic number rule. But now these has been EAN rule has been precised into a 18 electron rule, and today we are going to learn about the applications of 18 electron rule. So, before to start the 18 electron rule, this is the basic some basic terms which are used in organometallic chemistry. Generally, organometallic chemistry is the study of chemical compounds containing at least one bond between the metal and the carbon, right. So, either it including the alkaline alkali earth metals, alkaline earth metals, transition metal and other gases. Generally, the bonding of organometallic compounds are generally they are sometimes they are ionic, covalent, and the third one is a coordinate dative bonds are there. The stability of organometallic compounds is based on 18 electron rule, and organometallic complexes containing at least one metal and carbon bond, including the ligand like carbonyl ligand, nitrosyl ligand, then N2, PR3, hydrogen, and other number of ligands are there which are bind to the metal atom. History of organometallic chemistry. In the this is the pioneer molecule. It is called as Zsche salt, which is considered as a pioneer molecule in organometallic chemistry. Generally, the Zsche salt has a central metal ion platinum, and the oxidation state of a platinum in these is a +2. How to calculate that oxidation state? That has been shown by here. To calculate the oxidation state, I have used the simple formula, that is C is equal to M plus L. C is equal to M plus L, where C is the charge on coordination pair, where M is the charge on a metal, L is the charge on a ligand, and therefore, here the total charge of this complex is a -1, and it is equal to -1 is equal to M which is charge on a metal, that is oxidation state of charge on a metal, that is it is also called as the oxidation state of a metal, and minus the charge on a ligand. That means, here the ethylene ligand, three negatively charged chlorine ligands are there, and one is the ethylene ligand. Ethylene ligand is a neutral ligand, while this chlorine ligand, these three are anionic ligand. That means, they are containing -1 charge of each. There are 3 chlorine atoms, therefore total -3 is there. So, therefore, M is equal to +2, which indicate the +2 oxidation state of platinum in Zsche salt. So, history of organometallic chemistry, nature has also shown some organometallic complexes by its own. These are some naturally occurring is the vitamin B12, which is containing cobalt as a central metal ion. Before that, in 1890, NiCO4, that is nickel tetra carbonyl complex has been synthesized. Then after that, the Grignard reagent has been reported in 1900. And third one is a ferrocene, which is synthesized in 1951. Together, although with together of these artificially made some organometallic complexes, naturally occurring organometallic complexes are also found. This is vitamin B12. Then the as far as the basic terminology concerned, ligand and its nomenclature play a very important role to understanding the 18 electron rule, and these are some important ligands which are frequently used to whenever we are doing the study of organometallic complexes. First is the carbonyl ligand, which is a strong neutral ligand. Then second is the carbene ligand. Then carbon and metal triple bond is there. It is called as carbine. Then cyclopropylene, cyclobutadiene, cyclopentadiene. Then whenever 6 carbons are attached to the metal atom, then it is called benzene. Then 1,5-COD, then ethylene, and these are all are the ligands which are a different form of ligand which are used for the preparation of organometallic compounds. Then the one of the important term is the hapticity. Hapticity is a Greek letter, Greek symbol which is known as eta. What is hapticity? Hapticity is nothing but the number of carbon atoms of a ligand which are simultaneously bonded to the metal is called as hapticity, and it is denoted by the Greek word that is eta. Generally, the hapticity has been determined how much atoms which are attached to the central metal ion. Whenever one atom is attached to the central metal ion, the hapticity of molecule is 1. Whenever the more than one atom has been attached, it is shown by the dotted line, and that indicates the hapticity of attachment of a carbon atom to the central metal ion. Then, for example, I have shown here one simple example. For this is cyclopentadiene, and which is attached through one carbon atom to the metal. Therefore, it has a hapticity 1, while in this case this cyclopentadiene is here and there is a circle is there. That indicate it is attached to the 3 carbon atoms, and therefore, it has a hapticity of 3. While in this case the whole circle has been dropped inside the cyclopentadiene ring, it itself indicate the metal atom is directly attached to the 5 carbon atom. Therefore, it has a hapticity 5. So, in this way eta 1, eta 3 and eta 5, these are the hapticity which are allotted by the arrangement of atoms and arrangement of a metal and the attachment to the carbon atom. Okay. So, now we are going for the basic term of 18 electron rule. Generally, it is a rule that based on the facts, based on the valential electrons of transition metal. Generally, the transition metal has containing 9 molecular orbitals. That means that is 1 s orbital, 3 p orbital and 5 d orbital. That is 5 plus 3, 8 and 1 s orbital, that is total 9 molecular orbitals. One molecular orbital has been containing 2 electrons. That means the total capacity of s, p and d orbital is total 18 electrons, and therefore, whenever the molecule has occupied all 18 electrons in its s, p and d orbital, then these complex is said to be a stable, and that is a clear indicate, that is one of the thumb rule which is known as a 18 electron rule. And generally this means that there is a combination of 9 atomic orbitals, and again same things are mentioned here. When the metal complex has 18 valence electrons, it is said to be achieved the same electronic configuration as the noble gas, and the rule is some exceptions are there. So, we do not discuss the exceptions here, we are only try to understand 18 electron rule and its application. I have given you the comparison between the AN rule and the 18 electron rule which is used nowadays. Whenever the AN rule has been taken for the study, then it is the just summation of all electrons of the metal and the ligand. That means, whenever the metal has the atomic number is there, that atomic number plus the electrons contributed by the ligand, that is the summation of all these are nothing but the AN numbers. While in the case of 18 electron rule, instead of the whole atomic number of a metal, we have to consider only the valence shell electrons, valence shell electron of the metal and plus the electrons which are contributed from the ligand. This is the basic difference between AN rule and the 18 electron rule. Okay. So, I have taken the same example for our understanding, that is chromium CrCO6. Chromium has a total 24 electrons and plus the 6 CO. One CO has been containing 2 electrons, so 6 CO, that means total 12 electrons. So, number of electrons, the summation of all these electrons has been become a 36, while whenever we are applying the 18 electron rule, the valence shell electrons of chromium has a electronic configuration 3d4 4s2. That means, only 6 electrons are containing in the valence shell electron of the chromium. Therefore, these 6 electrons plus 6 carbonyl ligand, one carbonyl ligand has containing 2 electrons, and carbonyl is a strong neutral ligand. Therefore, 2 into 6, it will contain a 12 electrons. So, 12 plus 6 total become 18 electrons, and we already give try to understand the thumb rule, that is whenever the any complex has been containing 18 electrons, then it is said to be a stable. then it is said to be a stable, right. So, by using that 18 electron count, we can concretely say that this CrCO6 is a stable molecule on the basis of a 18 electron rule, right. Okay. So, both these rule has given the stability of the complex, but if the 18 electron count has been followed, then the complex is said to be a stable one, while the complex which is for 18 electron rule is a dimagnetic in nature, while if any electron has containing any one number of unpaired electrons, then if any unpaired electron has been available, then it is said to be a paramagnetic in nature. Okay. So, these are the different ligands and electrons contributed from the ligands is there. So, these are examples are there. In this way, the 18 electron rule play a very vital role to understanding, to determining the stability of the complex. This is all about the 18 electron rule and its applications. Laterally we are going to for the different videos regarding with the organometallic chemistry. Okay, thank you.